let's talk about one of the most intimidating ideas in math, the derivative. It sounds scary, right? But what if I told you it's a concept you pretty much already get? Seriously, by the end of this, you'll see it's not some big, scary monster. It just has a fancy name. Okay, this right here, this is the single most important idea to get. From this moment on, whenever you hear the word derivative, I want you to just swap it out in your head for a much friendlier word, slope. That's it. That's all we're talking about. A derivative is just the slope of a function. You know, the good old rise over run from algebra class. So, to really build this intuition from the ground up, we're going to run a little experiment. It's super simple. We're going to take a function, give one of its variables a tiny little nudge, and then we'll just watch and see what happens. And let's start with pretty much the simplest function imaginable. F of a equals 3a. If you were to graph this, it's just a perfectly straight line. And that makes it the perfect place to start exploring this idea of slope, or, the derivative.
So let's just plop ourselves down at some random spot on this line. We'll start where our input, the variable a, is equal to 2. Now, according to our function, the output, f of a, is just going to be 3 times 2, which is 6. Simple enough, right?
Okay, here it is. This is the core of our little experiment. What happens to our output, that number 6, if we just nudge our input a up by a teeny tiny amount? Let's find out. We started with a at 2. We're going to give it a tiny nudge of, say, 0.001. So now it's 2.001. Well, our function is 3 times that, which comes out to 6.003. Now hold on, look at that. The input changed by 0.001 and the output changed by 0.003. The change in the output is exactly 3 times the change in the input. Remember rise over run? That's literally what we have here. The change in the function's height, our rise, is 0.003. The change in its width, or our run, is 0.001. So if we divide the height by the width, 0.003 divided by 0.001, we get our slope. And that slope is 3. This is so important. At that specific point, where a equals 2, the slope, the derivative, of this function is exactly 3. It's a number that tells us exactly how much the output responds to a tiny nudge in the input. Okay, so we found this slope was 3 when a was 2. But was that just a coincidence? I mean, is the slope different if we check somewhere else on this line? Let's test it out. We'll pick a totally different spot. Let's head on up the line to where a is equal to 5. In that case, our function's output, f of a, is 3 times 5, which is 15. Now, let's do the same exact nudge experiment. We give it that same tiny nudge from 5 up to 5.001. And would you look at that? The exact same thing happens. The output goes from 15 to 15.003. The change is, once again, 0.003. The output still changes by exactly 3 times the input nudge. The relationship holds true. And this leads us to a really powerful conclusion. For a simple straight line like this one, it just doesn't matter where you are. The slope is always the same. No matter where you check, the derivative is always, consistently, 3. All right, so we've totally got the hang of this nudge idea. We get it. Now, let's connect that intuition to the formal way mathematicians write this stuff down. I promise, it might look a little weird, but you already know exactly what it means. So you're going to see it written like this, d f of a over dA. It looks kind of intimidating, but it's really just a super compact way of asking the exact question we've been asking. What is the slope of f of a when you give a tiny nudge? It's literally the tiny change in the output divided by the tiny change in the input. It's our rise over run. So now we can take our big discovery from a minute ago and write it out in the official language of calculus. For our function, f of a equals 3a, we can state with confidence that its derivative, d f of a over dA, is equal to 3. Now, just a quick, important little side note. For our experiment, we used a pretty small nudge, 0.001. In formal calculus, that nudge is actually considered to be infinitely small. They call it infinitesimal. But here's the cool part. Our intuition still works perfectly. The core idea is exactly the same. So, we figured it out. For a straight line, the derivative, the slope, is constant. It never changes. But that leaves us with a really fascinating question, doesn't it? What about something like a curve, where the steepness is literally changing at every single point? How in the world do you find the slope there? Well, that's the next big piece of the puzzle.